Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The subject of this lecture is cofactor expansion in calculating determinants. The plan is to tell you what cofactor expansion is, to give you an example of how you would use it, and then go through definitions and results with the aim of proving why it works. At the end, we will also prove that the determinant of A transpose is the same as the determinant of A. We have had earlier videos that go into some detail about determinant. There's one on definition of determinants using elementary products. There's another important one that proves why determinants are multilinear and alternating, whatever that means. And another video on the effect of elementary row operations on determinants. One proving that A is invertible if and only if the determinant is non-zero. And determinant of a product, AB, is the same as the determinant of A times the determinant of B. I will remind you of what we need for this lecture, but for more detail and more complete coverage, please watch those other videos. Here's an n by n square matrix. First row of it is A11, A12, A1j through A1n, and so on. To find the determinant of A, you choose your favorite row or column. You could do this with respect to any row or any column. You usually pick one that has many zeros. For each of the entries in that row or that column, you eliminate its row and column. When you do that, you will have a n-1 by n-1 matrix remaining, and you find the determinant of that. Multiply that by -1 to I plus j times aij. What's aij? aij is the entry in row I, column j, the entry for which we eliminate its row and column. I plus j is the sum of the row number and the column number. If the row number and column number add up to an even number, we don't do anything. But if they add up to an odd number, we multiply by -1. And then we add all the results. So we have 1 for each one of these entries, AI1, AI2, aij, all the way till ain. For every one of those n entries, you will find one of this -1 to I plus j times aij times the determinant of the remaining n-1 by n-1 matrix, add them together, and that's going to be the determinant of A. And that is called the cofactor expansion about row I. This is also known as the Laplace expansion. Here's an example. Here's a 4 by 4 matrix that I want to find its determinant by cofactor expansion about row 3. Why did I pick row 3? Because that's a row with 2 zeros, and that makes my life easier. I could have picked any of the columns or any of the rows. And so I will go through that row one by one. The 3-1 entry is 7, and the row number is 3, the column number is 1. They add up to 4, which is an even number. And so what I do is that I take -1 to the 4th, that's the sum of the row number and the column number, and that's just 1, times 7, which is the actual entry, times M31. Now, what's M31? M31 is the determinant of the remaining 3 by 3 matrix. And that's called a minor, by the way. So I find that. Now, you might say, how do I find the determinant of this 3 by 3 matrix? You could do cofactor expansion again. You could pick one of the rows or one of the columns and go through and do this process again. Then I go to the 3-2 entry or the 3-3 entry. Both of those are 0. And so when I multiply that 0 by whatever that minor is, I get 0. So there's no contribution for those. The last entry is the 3-4 entry. That's 4. And 3 plus 4. 3 is the row number, 4 is the column number. Add up to 7. And 7 is odd. So I will multiply -1 to the 7th by 4. 4 is that entry times M34. What is M34? M34 is the determinant of the remaining matrix when I get rid of that row and column. So that's the matrix 0, 7, -11, -1, 3, 1, -3, 5, 2. So the determinant is going to be 7 times M31 minus 4 times M34. I didn't finish it. You can finish that yourself. But again, how do you find the determinant of those 3 by 3 matrices? You could use other methods. You can use elementary row operations to find determinants, but you could also use cofactor expansion if you like to. Our main aim in this lecture is to show you why does cofactor expansion work. And that really depends on how you define determinants. You could actually define determinants via cofactor expansion. You could say the determinant of n by n matrix is what you get from this process, in which case you wouldn't have to prove that cofactor expansion works, but then you would have to prove other properties. What I have done in the series of video lectures is to define determinants via elementary products, and I will tell you what that is. Using that, I proved that determinants are a function on matrices that are multilinear and alternating. And I remind you of what that means also. From those, I proved all the other properties. And what I want to do is use those multilinear and alternating properties to prove that cofactor expansion works. Let me first set up the stage by giving you a little bit of vocabulary. So here's our n by n matrix. The ij entry of A, the entry in row I, column j, is aij. Now, if you eliminate that row and column, you're left with a smaller matrix, an n-1 by n-1 matrix. I'm going to call that matrix A sub ij. So A sub ij is that remaining n-1 by n-1 matrix. M sub ij is going to denote the determinant of A sub ij, and that's called the minor of entry aij. So for every entry, you have a minor, which means you eliminate the row and column and find the determinant of that smaller matrix. Cij is going to be -1 raised to the power I plus j times mij. I plus j is the row number plus the column number. Mij gets multiplied by -1 if the row and the column add up to an odd number. Remember, aij is a matrix, whereas mij is just a number. And Cij is just a number. And Cij is called the cofactor of entry Aij. The word minor and cofactor are universal. Everyone uses them the same way, but the actual letters that people use to denote these might be different from author to author. So here's an example. Here's a 3 by 3 matrix. The 2-1 entry, the entry in row 2, column 1 is a 2. And A21, the matrix that I get by eliminating the row and the column of that entry, is this matrix. The first row is 4, 7. The other one is 3, 6. This is the A21 matrix. And the minor of the 2-1 entry is the determinant of that. In this case, it happens to be 3. The cofactor of 2-1 entry is -1 raised to the power 3 times that determinant. So it's -3. But why is it -1 raised to the third power? Because 2, the row number, plus 1, the column number, is 3. If A is an n by n matrix, the row I, the row that you're going to do the cofactor expansion, maybe its entries are AI1, AI through AIN. Then for every one of those entries, you have a minor, the determinant of the matrix remaining after you eliminate the row and the column of that entry. And then you have cofactors, which are those minors multiplied by plus or -1, depending on whether the row number plus the column number is odd or even. The theorem that tells us what the cofactor expansion about row I is tells us that the determinant is going to be those entries in row I times their corresponding cofactors added together. That's the theorem that we want to prove. Let me remind you of some of the things that came in previous videos. So definition of the determinant, the way I define determinants is that if A is an n by n matrix, you find all signed elementary products and then add them together. The result is called the determinant of A and denoted by dit parentheses A. And what's an elementary product? Is a product of n entries, no two from the same row or the same column. That means you take your matrix and you place n non-attacking rooks on it. You pick n entries, no two of which are in the same row or the same column, and you find the product of those. You multiply them together. That gives you an elementary product. From that, you can get a signed elementary product. For each row of your matrix, the elementary product is going to have one entry. For row 1, it will have an entry in some column. You write down that column number. In the second row, you also write the column number. In the third one, you write the column number. When you write all those column numbers, you get a permutation of 1 through n. You get some ordering of 1 through n. Maybe the first one was in third column, so your permutation starts with a 3. This permutation could be odd or even, depending on the number of inversions that it has. An inversion is when a bigger number comes before a smaller number. So if in your permutation you have a 4 and then later on somewhere you have a 1, that's an inversion. You count that number of inversions. If the number of inversions is odd, your permutation is odd. If the number of inversions is even, your permutation is even. If the permutation is odd, you multiply it by -1. That will make it a signed elementary product. If the permutation is even, you multiply it by 1, and that will be your signed elementary product. So you find these signed elementary product, add them together, that's the determinant, that's the definition of the determinant. The most important property of determinants is that they are multilinear, or linear with respect to each row and column. What does that mean? If you have a whole bunch of row vectors, S R1 through Rn, so this is n plus 1 rows, and alpha is a scalar, then here's a theorem that I proved in a previous video. If you have two matrices and they're basically the same, they have the same rows except for possibly one row. This one row, the ith row, is different in these two, but everywhere else they're the same. If you take those two matrices, find their determinant, and add those numbers together, you get the determinant of the matrix that also has the same rows as those two, except for that ith row. And in that ith row, you just add those two rows. So the next property says that if you multiply a row by a scalar, you can bring that scalar out. These two properties together, linearity properties. And we say determinant is multilinear because it's linear with respect to every row, not just one row. It's also true that the same thing works for columns. If instead of those original row vectors, you had column vectors and you did similar things, it would work just as well. Now, the determinant is also alternating function of rows. So what that means is that if you switch two rows, the determinant gets multiplied by -1. If you have a matrix and all you do is switch row I and j, then the determinant gets multiplied by -1. Another way of saying the same thing is that if you have a matrix with two rows the same, then the determinant is 0. There's actually a theorem, which we don't need, but it's good to know, that the only multilinear alternating real valued function on square matrices with determinant of identity 1 is the determinant. So that would be actually the more conceptual way of defining a determinant, is to say that I want a function that takes n by n matrices and gives me a real number, and I want that function to be multilinear alternating, and I want the function applied to identity give 1, and then the only such function is the determinant. Now we're on our way to proving that cofactor expansion works, given our definition of determinant and the fact that determinants are a multilinear and alternating function. The first thing I'm going to do is this. Consider this n by n matrix and consider, what if I switch the ith row, that's the row that I'm interested in, and I'm changing that ith row and replacing that row with a whole bunch of zeros, then a 1 and a whole bunch of zeros. There's a 1 instead of the ij entry, and everything else is 0 in that row. Everywhere else, I kept it the same. And I'm going to call that matrix A. I want to know what the determinant of that is. The answer is that the determinant of this is exactly the same as the ij cofactor. It doesn't matter if you say the cofactor of this matrix or that original matrix. They're both the same. Cofactor is -1 to the I plus j times the determinant of aij, where aij is the matrix that you get by eliminating the row and the column of that entry. So if you have a matrix that has the ith row, 0, 0, then 1, then all zeros, then the determinant of that is going to be exactly just one cofactor. What's the proof of that? The first thing you do is step by step move that ith row to the first row. Switch the ith row and the I minus 1 for it. And then switch down with the next one up. And bring that one all the way to the top. But what happens to the determinant? Because determinant is alternating, every time you switch, determinant gets multiplied by -1. If that row was the third row, you would first switch it with the second one, then with the first one. You would have done 2 switches. If you're in the fourth row, you would have done 3 switches. If you're in the ith row, you would have done I minus 1 switches. So it gets multiplied by -1 to the I minus 1. Then the next thing you do is you take that jth column and move it to the first column. And you do that one at a time again. And again, because determinants is alternating with respect to columns, the determinant gets multiplied by -1 to j minus 1. What's the determinant of this guy that we end up at the end? If you use our definition of determinants, we have to find an elementary product. From this first row, the only contribution we get is if we pick that 1. All the other ones are going to be 0. So if you pick that 1 and eliminate its row and column, then you have to find the determinant of this remaining thing. That remaining thing is exactly aij. So the determinant of this resulting matrix is just 1 times the determinant of aij. If we go back to our original A, its determinant is the determinant of aij times -1 raised to the power I plus j minus 2. Why? Because starting with this matrix, I can go step by step to that matrix where the 1 is in the corner, whose determinant is the determinant of aij. And the only difference between that and this matrix is all the switches I did. And so I multiplied that by -1 to the I plus j minus 2. Now, I plus j minus 2 is either odd or even based on what I plus j is. And so I don't actually need that -2. It's just -1 to the I plus j. And that's the cofactor of ij. And so I'm done. That's the determinant of A, which is what I wanted to prove. Now let's prove the theorem about cofactor expansion about row I. So A is an n by n matrix, and row I of it I identified as AI1, AI2 through AIN. And I'm trying to prove that the determinant is the sum of those entries times their corresponding cofactors. Each one of those is a cofactor for an entry. What am I going to do? I'm going to start with the standard basis for Rn. E1 is a 1 and then all zeros. E2 is a 0, 1, and then all zeros. These are elements of Rn. They're not numbers, they are vectors. R1 through Rn will be rows of A. And Ri, the ith row, I can write it as AI1 times E1 plus AI2 times E2 plus AIN times EN. If I take AI1 multiplied by this row vector, this one by that row vector, that one by that row vector, and add them, I will get exactly row I. This is the determinant of A, except in the ith row, instead of writing Ri, I'm writing it in terms of that standard basis. But because the determinant is multilinear. I can bring all those coefficients out and I can split this up because all of these matrices have all their rows the same except for that ith row. So the multilinearity works exactly right and I get this. But now each one of these is one of those matrices that we saw before where its ith row is just 1, 1 and all zeros. And what we showed is that those are the various kinds of cofactors. So the determinant of those are all of the cofactors, and we get the result that we wanted. Finally, I want to prove that the determinant of A transpose equals determinant of A. I first want to note that cofactor expansion works for columns just as well as for rows in the same way. The theorem is that the determinant of A is the same as the determinant of A transpose. The proof is going to be by induction on n. If n is 1, I have a 1 by 1 matrix, and A and A transpose are actually the same. So their determinants would be the same. For n greater than 1, I'm looking at an n by n matrix. I'm assuming that I've already proved it for smaller matrices of size n minus 1 by n minus 1. I try to find the determinant of A by cofactor expansion about the first row, and I also want to find the determinant of A transpose by cofactor expansion about the first column. Now, the first row of A is the first column of A transpose, so those coefficients that I'm multiplying by cofactors are the same. But so are the cofactors. Why? The cofactor is a plus or minus 1 times the determinant of that n minus 1 by n minus 1 matrix. And determinant of such a matrix is the same as the determinant of its transpose by induction. So by the inductive hypothesis, those cofactors will be the same, and I'm multiplying them by the same thing and adding them, and therefore I will get the same. This is the end of this lecture. Like my video if you like it, subscribe if you want to be subjected to math videos at the undergraduate level on your feed, and keep hydrated at all times.